Welcome back. We are the day after our first test in this physical classroom. We still have a couple people that need to take that and make up today. So this week we are going to proceed with kind of this thing called the derivative. Some of the topics this week will be the derivative as a function itself. We've kind of already seen that in a sense. We had a distance, height, or position function. We had a new function from that called the velocity function. So we've seen a little bit of that. And then if we start with an original function, can we come up with a graph of the derivative, a graph of the second derivative? And if we are given the graph of the derivative, can we kind of go back the other direction? Can we come up with the graph of the original function? So those are some of the things that we're going to be doing. I will address Maple real briefly today. I did hand something out to the students in this classroom. Students taking this course on DVD later and students taking this course on cable TV, because of the fact that many of you are not physically near NC State and you're already paying a whole lot for this course, I don't kind of force you to buy Maple as well. So Maple is not a part of the cable course, nor is it a part of the DVD course. So when we address Maple in any way, shape, or form, it is not for the distance ed versions of this course. Section 2.8. Well, let me go back. Let me backtrack. I wasn't going to ask this, but I kind of will give you a chance. Anything on, well, not everybody's taken the test yet. Can't ask that. Okay, I'll ask that tomorrow. See if you thought there were any surprises. Don't answer that right now. 2.8 is the section we should be able to do justice to today in class, the derivative as a function. So we know how to find it. We've actually got a couple of ways right now. We don't have any shortcuts, but we have a couple of ways using the definition of derivative. First thing, and this is section 2.8. Derivative as a function. So we know what it represents. It represents the slope of the tangent line. It represents the instantaneous rate of change. We know a couple of ways by definition. I think probably the most often used definition of derivative, if we have f of x, we want f prime of x. And we'll still use this. Still has validity. And anytime we don't have a shortcut, we want to come up with a shortcut, we will come back to this in order to derive that shortcut. So that'll be our definition. We know what it is, slope of the tangent, but it is also a function. We have this new function called the f prime. So the first thing the author addresses in this particular section is, let's suppose that we have the graph of the original function. And let's say it looks something like this. So we'll try to make it kind of fairly smooth and continuous to start with, and then we'll see what happens from there. Let's say at this value, the slope of the tangent is 0. I'll just call that capital A. At this value, the slope of the tangent is 0. And at this value, let's call that B. And at this value, C, the slope of the tangent is 0. So if we're using this function, the picture of this function, to come up with another picture, the x value is still here on the x-axis, but this time the so-called y-axis is not a f of x axis, it's the derivative. So if I were making this transfer from the original function graph to a picture of its derivative, these are the points that I would locate first. Where are the places where the graph is, for lack of a better word, flat, meaning it's not on its way up, nor is it on the way down. It's instantaneously kind of sitting there. It's flat. So at this location A, the derivative should be what? 0. So I'm going to graph 0 on the derivative graph. So I'm picking values off of this, basically explaining what's going on the derivative from what's going on the original function. At B, what should be happening on the derivative graph?
0.
It should be 0 again. And at C, which is over here, the derivative graph should be 0. Is that okay? So those are 3 of the more important points. What is this graph doing to the left of A? It's increasing. And if it's increasing, what about the slopes of those tangent lines? They're positively sloped. Okay? Now, as you get closer to here, they begin to flatten out, right? They begin to get closer to 0. But all of the slopes of all of these tangent lines over here are all positive. So that's what we're graphing over here, is something that's positive. And at, near A, they ought to be getting closer and closer to 0 because these are getting flatter and flatter as we get close to A. So they're getting closer and closer and closer to 0. Is that okay?
Why did you draw it that? Why wouldn't you make it the slope being positive at A? You know what I'm saying?
Well, at A, the slope is 0. So
I mean,
this
like
is the slope.
approaching.
You mean like it kind of laid down and...
Yeah, why did you draw it the way you did?
Okay. So you want it to come down like this and just touch there and
Yeah.
be tangent?
Yeah, yeah, yeah.
Are you convinced that as we're getting close to this point, the slopes... Excuse me, that's not correct. Let me go back over here. As we get close to this point where it's flat, aren't the slopes getting more and more near 0? Isn't that happening right here? Are these values getting closer and closer to 0? And then, in fact, they are 0. Let me see if the next piece explains why it just kind of intersects here, and then we'll see what it does on the other side. As soon as we get on the other side of A, these are negatively sloped, right? Aren't all of these values, if we took a look at the slopes of the tangent lines, they'd all be negative. Is that correct? This tangent line right here is negative. This one right here is negative. This one right here is negative. Now, as we leave A, they're pretty close to 0. Slope of 1/10, 1/4, 1/2. And then they get steeper, negative. And then as we get closer and closer to B, they get closer and closer to 0 again. So is it okay to say they're pretty close to 0, and then they're pretty close to 0 again, and then they, in fact, become 0? Is that okay? Now let's go back to your question. Are the values fairly large positive values and then get smaller and smaller and closer to 0? Isn't that what happened here? We don't want it to just touch here, because if it just touched here, it'd probably go back up, right?
Right.
And we don't want it. We want it to now be negative because the graph is doing what? Decreasing. So where this is increasing, the slopes are positive. Where this is flat, it's 0. Where this is decreasing, the slopes are negative. Then the slope is 0 again. What happens after that point to the right of this B value, whatever B happens to be?
Increasing.
It's increasing again. So this piece of the graph is increasing. What about the slopes where something is increasing? Positively sloped. So they leave B fairly close to 0. The slope is fairly close to 0. Slopes are fairly steep here. And as we come into C, again, they're fairly close to 0. They flatten out. So fairly close to 0, they reach a value, some larger value where the slope is 4 or 5 or 8 or 15. And then they begin to get smaller again, and the slopes get closer and closer to 0. At C, the slopes actually are 0 at that instant. And what happens as we leave C and go off to the right? This graph is decreasing, which means that the slopes are what? Negative. And doesn't that graph continue to decrease? Therefore, this graph, the derivative, should continue to be negative.
How come you did it like curved before the A and you have a straight line after C?
It's not a straight line.
Okay.
It is curved. Yeah, this is all a curve.
Okay.
So, original function, and that's what we're talking about, the derivative as a function. If the original function is increasing, the derivative is what? Positive. Is that okay? Original function increasing, the derivative is positive. Original function decreasing, the derivative, this is the derivative graph, the derivative ought to be negative there. And if the original graph is instantaneously not increasing nor decreasing, it's flat, then that means that the derivative graph ought to be 0 at that instant. So what are we missing? We've got positive, negative, 0. What kind of derivatives are we leaving out at this point? Intentionally, by the way, since this is the first picture.
Triangular.
Undefined or does not exist. So we're not looking at those yet because those complicate things quite a bit, because there's a lot of ways that the derivative could fail to exist. And in fact, that's the next thing that the authors address. See why it's important to label graphs, by the way? That this is the f of x and this is the f prime. We're really talking about the same set of points in a way. We're talking about what's happening on the f of x graph, but we're using the f prime to do it. So it is a new graph, a new function. So if a derivative does not exist, what could happen graphically that would cause this to be the case?
Asymptote.
Could have an asymptote. So now I'm graphing the original function. So if we have a vertical asymptote here, let's say x equals a, the graph itself could do something like this. And the derivative does not exist at x equals a. In fact, the original function does not exist there. If you don't have a point there, then you're going to have a hard time talking about the slope of the tangent there. So the first derivative at a does not exist because there's a vertical asymptote. What's another way that a derivative could not exist?
So you couldn't draw a derivative graph for that?
At a, you cannot. Now, near a, let's see what happens. Maybe that will help solidify this topic. As we get closer and closer to a, what's happening to these tangent lines? They're getting steeper and steeper and steeper, right? Now, what does steep mean in terms of the slope of the tangent line?
It starts to get a little more positive.
positive, really positive, right? So these are, like the slope of this last one maybe is 15. And if I went closer to the asymptote, the slope might be 38. Closer, it might be 106. So it appears that the slopes on this side are getting infinitely large in a positive fashion. What happens here as we get closer and closer to A? Still positive, right? Positively sloped. Wouldn't it have to be positive because this graph is increasing, right? Then it has a little intermission, and then it's increasing again. So what about the slopes here?
They're still increasing.
Near A, they're positive infinity, right? So does it mean something graphically to say that the slopes are positive infinity? Possibly. But in terms of, is there a slope associated with this graph at x equals A? There is not. So the first derivative at A does not exist. This is one of the ways, is that it has a vertical asymptote. Here's another way.
On absolute values, not one.
Yes, absolute value, in fact, as simple a function as that is, it has something going on there, like an abrupt change in direction or a corner or a cusp. So if you had a graph that, let's say, did something like this, okay, it is continuous. By the way, this is not continuous, which leads to the problem. But here, this graph is continuous, but because of this little corner or cusp or whatever you want to call it, the derivative does not exist. Now, very different reason why it doesn't exist than here. As we come in from here, it looks like the slopes are kind of getting steeper. It doesn't look like they get vertical, but they're fairly large positive numbers. What about from the other side? They're not even positive anymore. They're negative, right? And they're not even close to one another. What you want to happen as you make this transition, let's analyze something like this. As you come in from both sides, you want the slopes as they come in from this direction to be the same or approaching the same value as if they came in from the other direction. So as you come in from both sides, you want the slopes to be approaching the same number. Certainly not the case right here, even though it's continuous. So the fact that there's a corner, the derivative does not exist there. So you said just a simple absolute value graph. That's correct. The derivative does not exist where? At the origin, right? So it doesn't have to be anything really, really complex for the derivative to fail to exist. So the derivative at 0 does not exist. Somebody want to explain that? Blair.
Whenever the slope of a line takes a dramatic change like that, it's going to produce a gap in the f prime of x graph. It's going to have a jump.
Okay.
It's not just going to be a continuous line.
So the slope is very different on one side of 0 than it is on the other. In fact, if we wanted to sketch the slope graph, the derivative function, what is the slope at every point over here? Not positive. I think we can be even more specific. It is positive because it's increasing. What else is it? It's 1. So the slope at every positive x value is, in fact, positive 1. Does that work? Now, I put an open circle there. Why did I put the open circle? Because we know we have a problem at 0. Is the slope at 0, is it 1? Is it negative 1, or is it something else? I don't know. I don't think you know either. I think it doesn't exist at 0. What's the slope at all these values right here? Slope is negative 1. And then the fact that we have an open circle when x is 0 is indicative of the fact that the derivative at 0 does not exist. So that's kind of what Blair said in words. Here's the diagram for it. Very abrupt change at 0. It's nice and predictable here, positive 1. Nice and predictable here, negative 1. We've got a problem at x equals 0. Derivative does not exist. All right, let's take a well-behaved function. We like them when they're well-behaved. Nice cubic polynomial. Let's find the derivative and then get an interrelationship between the original function and the derivative graph. Actually, before we find the derivative, let's see if we can sketch. Then we'll find the derivative, see if that sketch that we come up with for the derivative seems to be what we think it should be. How would we go about graphing x cubed minus x? Any suggestions?
Plug in values.
Plot some values? I think I would probably do something before that.
Factor out the x.
Factor it if you can. It does factor. Is that correct?
And factor that.
And then factor it again, right?
Well,
So the fact that we have 3 linear factors, does that indicate values that we can plot that are pretty important points that we want to make sure we plot?
Yeah.
So when x is 0, what's y?
0.
Okay. When x is, keep going with this list,
0.
1, y is 0,
Negative 1.
and when x is negative 1, y is 0. Those are probably 3 pretty important points because that's where it hits the x-axis. 0, 0, 1, 0, and negative 1, 0. Now what? Still, I'm not trying to find the derivative yet. I'm just trying to get a sketch of the original function. Blair.
Since x is cubed, we know to the right of positive 1 it's going to be increasing, and since it's not squared, it's not going to be increasing on the left side of negative 1, so it's going to decrease after that.
Is that all right? So values to the right of positive 1, when we put those values into this function, isn't the x cubed term basically going to win, going to dominate? So if we have 2 cubed minus 2 or 5 cubed minus 5, they're going to be positive. Is that correct? That's basically the same as somebody suggested plotting some points. That works the same. Okay, and that's not linear. That's a curve. But that kind of keeps going up. How do we know it doesn't turn and come back and hit the axis again? We found the only 3 intercepts that this graph has, right? So whatever it does the same thing from that point forward. How about between 0 and 1? Suggestion, plot a point. Maybe that'll work.
half.
Put a half in there. Either they're all positive or they're all negative, right? Because it's not going to go crossing the axis in here either. So if you put in a half cubed minus a half, that's negative, isn't it?
Yep.
So this is a sketch. I wouldn't call what I'm doing here a graph by any means. It's a sketch. In fact, most of my graphs are sketches. They're not accurate enough to be a graph. How about between negative 1 and 0? It's either all positive or all negative because it doesn't change in there either.
Positive.
Positive? Okay, you could try negative a half cubed minus negative a half, right? Positive? Again, I don't know how far up it goes actually, but I know it goes up and then comes back down. And how about to the left of negative 1?
Decreasing.
Decreasing. So actually, as you move from left to right, that'd be increasing, right? So as I draw it here, if you put in negative 5 cubed minus a negative 5, it's going to be negative, right? Very negative. But as you look at this graph from left to right, that's increasing, right? And it comes up to here somewhere, and it starts to flatten out, and then it's flat right there. Then it decreases. So is that pretty typical for a cubic polynomial? That's pretty typical, because they have like an S-shaped graph. That we'll call that typically an S-shaped graph. Three places where it hits the x-axis, 2 places where it changes direction. Could we come up with a graph of the derivative even though we don't have an equation for the derivative? I think we can. Somewhere between negative 1 and 0, this graph reached its peak, right? I think we can. Right now we'll call it something. Let's just give it a name and call it A. And I think before we're done with this problem, we'll be able to find out where that is. But at that place, it's 0. Somewhere between 0 and 1, we don't know exactly what that is. But at B, it's 0 again. Now let's use what we did on that first example. What's this graph doing? It's increasing. So the derivative should be positive. Again, that's not linear. That's a curve. At A, it's at 0. We already have that. From A to B, whatever those two values are, the graph is decreasing. If the graph is decreasing, the derivative should be negative. And then after B, the graph increases again. The slopes of the tangent line should be positive, therefore the derivative should be positive. That looks like it might be parabolic, right? It's pretty typical of what a parabola does. I don't know, this might be a little quick for this, but could we come up with a graph of the second derivative since we have a graph of the first derivative? So we would pick a value where this is 0. Let's say it's right there. What is this doing? Decreasing. So this should be negative, right? Here it's 0. We already have that. Here it's increasing. So it should be positive. Does that seem like that should be the case? Here's a cubic polynomial. We found its derivative graphically. It looks like it's quadratic second degree. And here's a derivative again, and it looks like it's first degree, right? Linear. Let's, I know it's a little bit of a battle, but I think we've done this enough where we can go pretty quickly. Let's take this original function and see if this seems to make sense with the actual derivative once we find it. I know some of you know the shortcut. Tell me what answer we're going to get before we 3x squared minus 1, right? Some of you are saying, oh my goodness, how did you know that? But a lot of you, I think, know that. But we're going to do this, and we'll have some shortcuts here. We're going to do this the so-called long way. So the function at x plus h is that. Is that correct? From that, we'll subtract the function at x. all of that over h as h approaches 0. Let's cube x plus h. What's the first term? Next term?
3x squared h.
Next.
3x h squared.
We're going to subtract x. We're going to subtract h. We're going to subtract x cubed. We're going to subtract a negative x. Do we lose any terms at that point in time? Good. X cubed minus itself plus x minus x. What else happens? Everything has an h
Yeah.
in the numerator. Let's factor it out front. Let's factor an h out of that. What do we get? Minus 1. Is that everything? As long as h is not 0, which it is not 0, h over h reduces to 1. And we're saving the limit part to the very last step. So it doesn't affect 3x squared. It doesn't affect minus 1. But h approaching 0 causes that term to disappear and that term to disappear. So we have a new function, a quadratic function. Is that at all close to what we came up with before we even had this equation? We came up with this picture right here. Could that be the sketch of 3x squared minus 1? Okay, we come down 1 unit, right? And then 3x squared means it's a parabola that opens upward that's a little skinnier. Now mine probably looks like it's a little fatter than it should be, but that's certainly the right shape. Now I said once we had this, could we find out what A and B actually are numerically? Set it equal to 0, right? We want to know where the f prime graph cuts the x-axis. Where is the f prime graph equal to 0? So we'll take that equation and solve it. It's not going to be nice, clean values. So 3x squared equals 1. X squared equals 1/3. So x equals plus or minus square root of 3 over 3. If you rationalize, that's not necessary. You could just say 1 over the square root of 3. Which is approximately square root of 3 divided by 3, 0.577. Somebody check that for me. How's that work? Thank you. So back to our graph of A and B, that little parabola that opened upward. A apparently was the one on the left, negative 0.577, and B was positive 0.577. So once we have the actual function, we can find those numerical values. We're not that far away from this. So somebody that knew ahead of time the derivative was going to be 3x squared minus 1, how'd you do that?
Exponent times coefficient.
Bring the power down.
Minus 1.
Okay, good. Several of you know that. So let's give everybody the same advantage. Now, it's not in the book yet, but we're going to get to it very quickly. All right, so Alyssa, right? So you said exponent. So exponent is 3, x2, x to the second. 1 degree less? So there's our 3x squared term. And how about the derivative of minus x? Minus 1. You could use the same rule, but I mean, you think about the line, just the line by itself, minus x, doesn't have slope negative 1, right? So several people were saying what the answer was going to be before we got it. That's the shortcut they were using. A power rule or an exponent rule. We're about to get to that point. But I guess the purpose of this example is we started out with a kind of a rough sketch of our original function. From that rough sketch, can we get a sketch of the derivative? Yes, we can. And in fact, we could get a sketch of the derivative of the derivative, the second derivative. And we could do third derivative for that matter. What would that be? What's the slope all the
One.
time?
Maybe 1.
Be 6.
It's constant, right?
Yeah. 6.
Be some constant value. So mine might look like it's 1, but it's a sketch. It's rough.
6.
So it would be, some of you are going ahead, it would be 6, right?
Yep.
It'd be constant, the next derivative. What about the derivative after that?
0.
It'd be 0, and it'd be 0 forever after that, right? I'm not, some of you aren't looking at me with a very nice, that was probably too much. Sorry. So you're really responsible for right now, if you had a graph of the original function, can you come up with a graph of the derivative? All right, we started with a polynomial. We always do that because they're easier. Let's go to something that's not polynomial. It's still relatively kind. What's this thing look like?
1 over 2 times square root.
Okay, that's the derivative, but just this original function, what's it look like? Okay, JT?
Curve to the right.
Okay, and it is actually, I guess you could describe it as half of a parabola, right?
Yeah.
Because the other half would be down here. We don't want that. We just want the principal square root. I don't know that my graph is really that good here, but let's see what we think happens. As we get closer and closer to 0, what's happening to these tangent lines?
Decreasing.
Aren't they getting steeper? Right? And steep means what? It means trouble, for one thing, because the slope of something that is as steep as it can get, which would be vertical, what's the slope of a vertical line? Undefined. So if my graph were really, really accurate, they would show these getting really, really steep to the point where they're pretty nearly vertical, and in fact, very close to the origin. They're about as close to vertical as you can get. So the derivative, the derivative at 0, if they're getting steeper and steeper and steeper, at 0, they're basically vertical. What's the slope of a vertical line? Undefined, does not exist. So think about these numbers that we're getting. The slope right here is maybe positive 52, right? And then it's positive 20. And then it's 7. And then it's 1. And as you work your way out here, it's 1/2. And as you work your way out here, it's 1/4. They're all what? Positive? Is that correct? Because the graph is increasing. So if this graph is increasing, what is the derivative graph got to look like? Positive, right? The original function is increasing. The derivative is positive. And I guess we could just kind of pick off some numbers. They're very, very positive, right? Near 0, because it's very steep. And then they're getting less positive. Will they ever be flat in a sense that the derivative is 0? They get very close to that, though, right? Does that look like what the derivative graph might look like. It's positive. This whole thing is increasing. This whole thing is positive. This one is never flat. This one is never 0. It never does hit the x-axis. Although as you work your way out to the right, it gets closer and closer to 0. Isn't that what happens here? Closer and closer to 0. So this might be the relationship between these two. So by definition, the derivative, we know it kind of looks like this. Let's kind of validate that. The function at x plus h minus the function at x all over h as h approaches 0. What's the process that I need to go through to simplify this? Have we done this? Okay. Multiply by the conjugate. Can't just do that to the numerator without also doing it to the denominator. So how does that simplify the numerator? What happens when you take this binomial?
Removes the radical.
Okay, removes the radical, actually eliminates the middle term too, because it ends up being the first term squared minus the second term squared. Is that correct? Well, that simplified the numerator a lot. Denominator's kind of a mess. So x plus h, drop out the x. The numerator is just h. As long as h is not 0, h over h reduces to 1. Again, we'll save the taking of the limit till basically the last step. What's that denominator become as h approaches 0? That term right there kind of disappears, doesn't it? So the square root of x plus h becomes very, very close to the square root of x plus 0, which is just the square root of x. So if this is the square root of x, and here's another one, what's the denominator? 2 square roots of x. Now, I know a lot of you know the shortcut. Is that what you expected?
Yes.
And is this graph is that what that would look like? Right? X can't be 0 because then we'd be dividing by 0. If you put in a positive number, which you have to put in for x, right? Can't put in a negative number. That's why the graph doesn't exist over here. And as you put in larger and larger values of x, the graph is getting smaller and smaller, but never 0. So that seems to be a pretty good match there between those two. All right, you will see a variety of notations in this book. Some of them we've already used. Some of the others, just in case you see them. We have used this. We have used this. I don't think we've used this yet, but we're going to use that a lot. Derivative of y with respect to x, dy over dx. It's first derivative. That's all it is. The derivative of f is the same thing, or derivative of f of x with respect to x. These are just different notations kind of accumulated through time. Everybody kind of put their own stamp on this. Derivative of f of x with respect to x. Derivative of y with respect to x. Those all mean the same thing. Just different notations accumulated along the way. Derivative of y with respect to x at x equals a. We have a better way of doing that, I think. And that's just say, what's the f prime at a? but those are both notations. All right, last thing today. If a function is differentiable, the only way that it could be differentiable is that it actually had points at all the different x values. It has to be continuous. So if we know for a fact it has a derivative there, it must be true that it is continuous. If I were to change these around, is the converse of this true? If it is continuous, does that guarantee the fact that it would be differentiable? Not true. Okay? And you can probably come up with numerous pictures. Just because it's continuous, well, it could look like this, right? It could have some kind of an abrupt change in direction, a corner. That is certainly continuous, but it's not differentiable. But the other way around, if a function is differentiable, if we know that for a fact, then we know it's continuous there. Okay, and I want us to do one more thing, which we'll start class with tomorrow. Contrapositive. What's the contrapositive of this, and should we expect it to be true? All right, see you tomorrow.